Hello, my name is Yang. I come from Intel SDN team. I'm a Senior Software Engineer. My topic is integration of Opendaylight service function chaining and vector packet processing. Here is my talk's agenda. First, I will talk why Intel integrates Opendaylight SFC with VPP. Second, I will introduce service function chaining, illustrate Opendaylight SFC architecture and VPP integration architecture, and elaborate work processes. Third, I will introduce my demo's network topology and configuration. Then I will demonstrate how Opendaylight SFC and VPP work together. And last, I will have a summary. We arrange a Q&A session in the end, so please keep your questions in Q&A session. NSH is a special protocol for service function chaining. Intel developed NSH patches for vSwitch to support service function chaining. Current Opendaylight SFC depends on these vSwitch patches, but people is complaining these NSH patches are not in official vSwitch release. We are still struggling to push these NSH patches to vSwitch community, but it's very slow to merge them. Moreover, this NSH implementation is the only one available solution for SFC. People want more choices. Fortunately, Cisco open-sourced VPP in Fedor project. VPP is a high-performance DPTK-based dataplane implementation. Its value proposition is consistent with Intel's. DPTK is the acronym of Dataplane Development Kit. It's an Intel open-source project. It can boost packet processing performance and throughput. VPP, NSH, SFC, and Honeycomb projects released 17.01 in this January and February. These official releases can support NSH very well. At the same time, Honeycomb project provides Opendaylight-friendly netcov and restcov APIs. So Opendaylight SFC can configure VPP dataplane by Honeycomb netcov APIs. By the way, NSH SFC project implemented NSH protocol, NSH SFC plugin for VPP and Honeycomb. Honeycomb project implemented netcov and restcov APIs and can interoperate with VPP by VPP Java APIs. Based on the above problems and opportunities, we started integrating Opendaylight SFC and Fedor VPP. This diagram illustrates service function chaining. What's service function chaining? IETF SFC draft has a standard definition. The definition and instantiation of an ordered set of service functions and subsequent steering of traffic through them is termed service function chaining. In SFC architecture, there are classifier, service function forwarder, and service function. Classifier will encapsulate the traffic from the client with the NSH header and steer the traffic to the first hop, service function forwarder, in the specific service function chain. We call specific service function chain rendered service path, i.e. ISP. Classifier also will decapsulate the reverse traffic and steer the reverse traffic to the original client. Service function forwarder will steer the traffic to service function or next service function forwarder or classifier according to network service path and network service index in NSH header. Service function is a specific service such as firewall, DPI, load balancer. This is Opendaylight SFC architecture, VPP classifier and VPP renderer here. When a user creates ISP by SFC UI or REST call, the information will be saved into SFC data store. VPP classifier and VPP renderer are listening to SFC data store, so they can get the information and call netcode APIs to configure VPP node, such as creating bridge domain, VxLAN-gpe interface, NSH entry, and NSH map. By the way, bridge domain is similar to bridge in OpenVSwitch. It's a layer 2 broadcast domain. VxLAN-gpe is a VxLAN generic protocol extension. It's a kind of tunneling protocol similar to VxLAN. NSH entry includes network service path and network service index information. NSH map will map the specific NSH entry to VxLAN-gpe interface and specify how VPP should handle NSH header. You will see what they look like in the demo. This is Opendaylight SFC and VPP integration architecture. VPP renderer and VPP classifier will call honeycomb netcode APIs to create VxLAN-gpe interfaces, NSH entries, and NSH maps. Honeycomb will save this configuration data into honeycomb data store. Honeycomb translation layer will translate the configuration data into related VPP Java APIs calls. VPP will execute these APIs. For VxLAN-gpe, VPP will call VPP call functions to create a VxLAN-gpe interface. For NSH entry and NSH map, VPP will call NSH SFC plugin functions to create NSH entry and NSH map. This is my demo's logical topology. We used VPP to play classifier and service function forwarder rules. Every box is a Vagrant VM except web client and web server applications. This is physical topology and configuration. VM1 and VM6 are classifiers. Web application uses Ethernet interface VETH-AMP and host VETH-BR are VETH pair. Host VETH-BR is attached to bridge domain SFC VPP. Classifier will encapsulate the traffic from web client with NSH header and send it to the VxLAN-gpe interface. VxLAN-gpe interface will end VxLAN-gpe header and send it to the gigabit Ethernet interface. Classifier also decapsulates the reverse traffic from web server and send back the packet to web client. VM3 and VM4 are service function forwarders. Service function forwarder has 3 VxLAN-gpe interfaces. They correspond to classifier, service function, and the next service function forwarder, respectively. All the interfaces are attached to bridge domain SFC VPP. All the traffic from and to service function forwarder will go through this gigabit Ethernet interface. The blue network is a data plane network. The black network is a control plane network. Opendaylight SFC is running in the host machine. It configures service function forwarder and classifier via control plane network. In my demo, I created two ISPs. One is for the traffic from web client to web server. The other is for the reverse traffic from web server to web client. The forward traffic will start from web client, goes through classifier 1, VPP1, SF1, back to VPP1, then to VPP2, to SF2, to back to VPP2, goes through classifier 2, and then arrive at web server. The reverse traffic is similar, just follow reverse path. This is a logical topology for my NSH proxy demo. I added NSH proxy VM between SF2 and VPP2 because this SF2 is a legacy service function. It cannot support NSH header. So here, SF2 is special. The forward traffic from VPP2 will go through NSH proxy first. NSH proxy will decapsulate the packet and remove NSH header, then use VxLAN to re-encapsulate the packet and send to SF2. NSH proxy saved this NSH header, so when SF2 send back the VxLAN packet to NSH proxy will decapsulate it and re-encapsulate it with VxLAN-gpe and the saved NSH header, then send back the packet to VPP2. The process is similar for reverse traffic. So now let's start a demo. Here we start Opendaylight SFC. Install VPP renderer. VPP classifier and SFC UI. Then we need to check network connector has initialized. Not yet. Wait a second. Here network connector has initialized successfully. Here we run SFC 104 demo with NSH proxy. This Python script will start VPP classifier VMs and VPP service function forwarder VMs and service functions and NSH proxies.
Then it will call Opendaylight SFC REST call for APIs to create ISPs and configure VPP classifiers and VPP service function forwarders. It will take a long time, so we skip the processes. Here you can see SFC 104 demo has finished. Here web client pin web server. It's okay. Web client wget web server is also okay. Now let's log into classifier 1. Show VPP interfaces. Here you can see VxLAN-gpe interface and VETH interface. Every interface is receiving packets and transmitting packets. Let's show VxLAN-gpe interface details. Here you can see local IP, remote IP, VNI, and the next protocol. It's NSH. Let's show NSH entry. You can see service path and the service index, metadata type, and the next protocol. And NSH context header. Here we show NSH map. NSH map maps NSH entry to VxLAN-gpe interface and specify NSH action. Here you can see map correspond NSH entry. NSH action is push and me is push NSH header. Then kept by VxLAN-gpe. So let's log into SFF1. Here is the interfaces for service function forwarder. We have 3 VxLAN-gpe interface. Every interface is receiving packets and transmitting packets. Here is the VxLAN-gpe interface details. Local IP is the same. Remote IP is different. Here is the NSH entry. NSH map. VxLAN-gpe interface where NSH entries and NSH maps are created by Opendaylight SFC. Okay, let's log into SF1. Here you can see VxLAN-2 Python script. This Python script emulates NSH aware service function. Let me check what it is doing. You can see it is processing NSH packets. This is reverse ISP. This is forward ISP. Let's log into SF2. It also has 3 VxLAN-gpe interfaces. Every interface is receiving packets and transmitting packets. Right. Here is NSH entry, NSH map. Let's look into SF2 proxy. It's a NSH proxy VM. Here VPP plays NSH proxy rule, so we can say VPP interface. Here we can see VxLAN-gpe interface and VxLAN interface. VxLAN-gpe interface is for service pattern forwarder. VxLAN interface is for service function. Let's log into SF2. SF2 is a legacy service function. We also use VxLAN-2 Python script to emulate NSH unaware service function. Let's check log. Here you can see SF2 is processing VxLAN packets, not NSH packets. Here let's log into classifier 2. We can see VDTH interface and the VxLAN-gpe interface. Every interface is processing packets. Let's show NSH entry and NSH map. You can see NSH action is pop. That means remove NSH header. Okay, demo is done. Thank you.
Here, let's summarize the information I want to deliver to you. Opendaylight SFC has enabled pure VPP-based service function chaining solution. Now, users have two choices, Open vSwitch and VPP. Both of them can use DBDK to accelerate NSH-based service function chaining. We welcome you all to join our developer community and optimize service function chaining performance and maximize Intel hardware platform's value. Please refer to the below resources if you want to know more technical details. Thank you for your attendance. Now it's time for Q&A. Please ask your questions. Thanks.